So forces in fluid. So there are 5 forces are acting. 5 different forces. One is pressure force and gravitational force, viscous force, turbulence force, compressibility force. In fluid kinematics, I think we have 4 or 5 mathematicians have given the equations, right? For example, first one, Reynolds transport theorem. So in Reynolds transport theorem, so we are going to neglect the compressibility force, right? We will consider only the pressure, gravitational, viscous and turbulence. And second one, Navier-Stokes equation. So in this we are going to neglect turbulence force and compressibility. So you will have only these 3 things: pressure, gravitational and viscous, right? Third one, Euler's equation. Euler's equation, we are going to remove the viscous also. So finally we will have only the pressure force and gravitational force, right? So from the Euler equation only we are going to get Bernoulli's equation. So we know what is Euler, where it is applied, right? So in a streamline, so streamline, we know that what is a streamline? A streamline, it is an imaginary line, right? So on this line, it is an imaginary fluid flow line, right? So on this line, if you point a mark and draw a tangent to this imaginary line, so it will give you velocity and its direction, right? So this line is streamline. So here only we are applying the Euler's equation, right? Euler's equation, right? So, and one more thing, if a fluid flow over a solid body, right? Flow over a solid body, when it interact with this solid body, right? So you may have some resistance, restrictions, right? So that is nothing but shear resistance. So that effect is, we call it as viscous effect, right? So that effect will be eliminated after some level. So up to this may be viscous effect there from the solid body to here. So after that, so the flow may be having inviscous effect, non-viscous effect, right? So these are all the streamlines, right? These are all the streamlines which are parallel to each other, right? And as I said, it will not have any viscous effect, right? So these kind of non-viscous streamlines only suitable for this equation. right? Bernoulli's equation can be applied for these kind of non-viscous region or inviscid fluid flow region only applicable, right? So pressure force and gravitational force only will be applied in Euler's equation. So from the Euler equation only we will get Bernoulli's, right? So we know that Newton's law, F into ma, here the acceleration ma, here the acceleration will be dv by dt, right? Or else we can write like this: dou v by dou s ds by dt plus dou v by dou t, right? So this will become dou v by dou s into v plus this component will be 0 because we are the streamline definitely will be a steady flow. So steady flow is nothing but properties with respect to time is equal to 0. So finally your acceleration will become like this. So this is your acceleration, right? So force is equal to mass into acceleration, right? So if you take a streamline, right? If you take a streamline, just pick a single particle, single fluid particle, right? In a streamline, you just take a single fluid particle along the streamline, right? So in this streamline, so what are all the forces? I already told you that. So the streamlines, especially in Bernoulli's equation, we are dealing with the streamline which is having no viscous effect, right? So no viscous effect means, so what are all the other force except viscous force? What are all the other force acting on this fluid particle? If you look at, one is P into dA, because dA is nothing but the area of fluid particle, right? And one more force is acting opposite to the so which this is reactant force. So P plus dP into dA, right? So these are all the two forces, and one more thing is the self weight of this particle, fluid particle, W, right? So which will have some angle, which will have some angle. So if you make a normal line, so between the self weight direction and the normal line will make some angle, right? So if you solve this forces. So P into dA, right? This is acting force. And this is your reacting force. So that's why we are using negative sign, because it is a reactive force. And one more force is acting downward, that is self weight will become W sine theta. Why? Because if you make a triangle like this, right, your self weight is here, this is your W, theta will be here, right? So this is your S direction. So this is the flow direction is S, we are saying it is S, right? And this is Z direction, and here it will be X direction, dx, right? The displacement in X direction dx, displacement in Y Z direction dz, displacement along S direction ds, right? So W sine theta is equal to mass into what we have seen in the acceleration, right? V into dou V by dou S is for single fluid particle, but you can write here V into dV by ds for whole section, right? For whole amount of fluid, right? For all the streamline you can take like this. For if it is single fluid particle means you can use a dou symbol, right? For the domain, right, for the whole amount of liquid you can use d, right? So total derivative, that is partial derivative for single fluid particle, total derivative for all over the domain, right? So next one, the PdA will get cancelled. The equation will become like this, dPdA minus, you can write W like this, rho g is your mass, sorry, rho dA ds is your mass g. So if you join with g, so it will become weight. Sin theta, you can write sin theta like this, dz by ds, dz by ds is equal to, so here also the same conversion, rho dA dz into V into dV by ds, right? So now if you remove dA from the equation, right, so it will become like this, minus dP minus rho g ds get cancelled, so you will have only dz, as we are going to remove the dA already. And finally here dz ds get cancelled, rho v dv, right? So area already removed, commonly removed, right? So this is your equation. So if you commonly divide it by rho, again divided by rho, it will become minus, and also you can remove the negative symbol when you join like this, is equal to 0, right? So if you integrate it for a whole domain, right, integrate it for a whole fluid particle which is occupied the streamline, right? So dP by rho plus g dz plus V into dV, right? So equation will become like this: P by rho plus GZ plus V square by 2, right? So this is your Bernoulli's equation.